Everybody, this is Bob Devance, K5CRX for the McKinney Amateur Radio Club. This evening, we'll be taking up session 3 of our licensing class that we've been working on the last couple of weeks, working on the Amateur Extra License Exam Prep, covering primarily the technical subjects of that particular exam. We'll be picking up where we left off last week when we're talking about digital excitement, as they call it, digital techniques for amateur radio. And then from there tonight, we'll be looking at modulation techniques, amplifiers, and power supplies. This session will be considerably more technical than some of the previous sessions, a lot of technical jargon and other such things. And we'll try to take as much time as we need to talk about the terms and make sure that you're comfortable with those and you understand the questions as well as the answers. With that, we'll be starting just momentarily, so be ready and stay tuned. Okay, let's get started here. We'll go back to let's see, digital excitement with your computer, dealing with some of the digital subjects that are popular with amateur radio these days. We'll pick up where we left off last week, which is about, 10 or 15 questions, whatever, something like that into it. We'll pick that up and finish it, and then from there, we'll launch the new section as we talk about modulation and power supplies and some other technical subjects. So with that, let me share my screen, and we'll get it rolling. And put it in, let's see, slideshow. Come on, slideshow from the current slide. There we go. Okay. Speaking up just about 2 questions before where we stopped last time, just felt like it might be kind of nice to have this available there for us to look at again. We talked about the Baudot code and the ASCII code. Baudot is a 5-bit code, whereas ASCII is an 8-bit code, of which 7 bits are normally used for the data. The 8th bit can be used as a parity bit when necessary. The great difference between those two then is that the Baudot code with only 5 bits does not have upper and lower case in one character set. It has 2 character sets. You use a special code that we send to the receiver that says we're going to do things in uppercase, or another code that says lowercase, and it will shift accordingly. The ASCII set, however, has both upper and lower case and all the symbols built into a single set. So that makes it kind of nice in dealing with that. So the differences between that is Baudot uses 7 characters. Baudot uses 5 characters, ASCII 7 or 8. Baudot uses 2 characters and letters as shift codes, whereas the ASCII includes all the characters. Okay, which of the following synchronizes WS, JTX, and the X being any of those programs that run under the JTX program? The digital transmitting mode for timing, and of course, we have to have our computer clocks carefully synchronized. For example, on FT8, that your computer clock needs to be within a second of Universal Standard Time. Okay, an ARQ is, how does that accomplish error correction? If errors are detected, then it requests a resend. That's what the ARQ means, automatic repeat request. It sends a request to repeat the previous packet. ARQ is part of the Pactor and the Clover formats. Okay, which digital code allows only 1 bit to change between sequential code values? This was one that brought back some memories. I had to dig into the gray matter a little bit on this one. It's the gray code. Most of the binary codes, rather, will on certain transitions from one number to the next, will change several bits at one time. For example, when we go from a binary 3 to a binary 4, 011 is a binary 3, 100 is a binary 4, and so you can see that from the 3 to the 4, actually all 3 binary bits changed. So to avoid that and to make things a little faster and make the transitions a little better, we use the thing called the gray code. The gray code is a special layout of the binary code so that we only change 1 bit at a time from character to character. And back up just a moment, as it mentions here, this helps to reduce the bandwidth. Okay, orthogonal frequency division multiplexing, a technique used for which type of amateur communications? Remember, anytime you see orthogonal, that has to do with generally 90 degrees or angle shifting. So that's being used with the various digital modes. Okay. What describes orthogonal frequency division multiplexing, and that is a modulation technique using subcarriers at frequency chosen to avoid intersymbol interference. All that simply means is that we're using various subcarriers of the center frequency, primarily of an FM signal. If you think about it, on the commercial FM broadcast radio stations, they will often use one of their subcarriers, which is just a carrier spaced a little ways away from their primary carrier. And on that subcarrier, they carry a totally different programming. One radio station that we listen to does that. They have a teaching station set up on one of their subcarriers, and it's strictly just teaching, while the main radio station is running music and announcements and programs of all kinds. We can do that same kind of thing here with amateur radio. What is quadrature amplitude modulation? QAM. Quadrature should be a key there. We're talking about angles and 90-degree things. Transmission of data by modulating the amplitude of two carriers of the same frequency, but at 90 degrees out of phase. Quadrature amplitude modulation. We're actually changing the height of the wave that's going out, which is the amplitude portion. Which of the following is characteristic of FST4? I've not dealt with FST4 personally. I don't know a whole lot about it, but apparently it's a really good mode for use in the lower frequencies. This is one of those wonderful questions where everything is correct. Four-tone Gaussian frequency. We'll talk more about Gaussian here in a second. Variable transmit-receive periods, the 7 different tone spacings that it can use. Okay, and then this just talks a little bit more about it. Move one thing on my screen there. Okay. As they mentioned here, used often on the lower bands, 2,200 meters and 630 meter bands. Now, those translate into 136 kilohertz and 475 kilohertz, which are very, very low frequencies, obviously, or VLF frequencies. And this particular FST4 apparently works really well on those lower frequencies. Okay, the Gaussian filter that they mentioned produces a waveform as you see there on the right. That's the idea behind it. Gives a nice bell curve to it so that we have a nice sharp frequency response. And that's used Gaussian frequency shift keying, part of frequency shift keying. What is one advantage of using an ASCII code for data communications? Well, since we have that 8th bit hanging out there that we can use as a parity bit, then that allows us to have we transmit upper and lower case together. It also, that has that 8th bit, by the way, which we can use for parity. That's not the answer they're looking for here. It has both upper and lower case in one character set. Advantage of using parity bits, that's where I was getting ahead of myself. Allows a little bit of error correction. It's not a sophisticated error correcting technology, but it does work just a little bit. Parity, by the way, is where we take that last bit, make it a 1 or 0, and it's predetermined on how we're going to determine that. For example, if it's a 1 bit, it may indicate that there is an odd number of 1 bits in that particular character, or it can be a 0, meaning there is an even number of 0 bits, however it happens to be defined. So, but anyway, by looking at that parity bit and then counting the number of bits that it describes, we can do an elementary form of error detection. Bandwidth of an FT8 signal, this is one you just have to remember, it's 50 hertz. Very narrow bandwidth for FT8, which is a good thing. Bandwidth for a 4800 frequency shift, 9600 baud ASCII FM transmission. Again, this is one I recommend. Just remember the answer. Now, the next slide will show how we calculate that. But since we're going to have a lot of questions dealing with that calculation, I think the easy way to do this one is just remember the 15.36 kilohertz. The way it's calculated, we take the baud rate, which is 9600, times 1.2 times the 4800 rate. Gives 15,360. Moving the decimal point over 3 places gives us 15.360 kilohertz. Again, probably easiest just to remember the answer for that one. Which of the following HF digital modes uses variable length character encoding? That's the PSK31. You'll recall the PSK31 allows us to actually carry on conversations, keyboard to keyboard, as we call it, digital conversations. It uses variable lengths of the characters, much like Morse code does. As you'll recall, Morse code letter E is a dit. Morse code letter H is four dits, four dots. And so we see those characters that are most commonly used given shorter lengths. The same is true with PSK31. How can data rate be increased without increasing the bandwidth? Basically, we use a more efficient digital code. We use one of the codes like the gray code we talked about earlier, something like that, to be a little bit more efficient. What technique minimizes the bandwidth of PSK31? Using sinusoidal data pulses, and as opposed to a square wave for the data pulses. By rounding those edges a little bit, it tends to conserve the bandwidth. It doesn't take as much bandwidth to transmit it. Which of the digital modes has the narrowest bandwidth? Our good friend FT8, 50 hertz, remember? What digital protocol is used by APRS? You remember that's the thing that reports your position and where you are. It's AX25, which is a derivative of X.25 or X.25, used in the commercial world for a lot of different things. Okay, what type of packet frame is used to transmit APRS beacon data? It's called unnumbered information. It sends the packets out almost at random. They're not totally random, but it's almost randomized. Oh, let me back up. There's one little thing to mention here just for your information. This terminal node controller, or TNC, is part of the APRS system. It hooks to the radio. The radio receives the information. The TNC processes it and retransmits it back out on the same frequency. And then it goes to a larger collecting repeater someplace else, or digipeater as they're called, and will eventually find its way into a worldwide database with which we can track different people who are reporting by APRS. They mentioned the GPS equipment. Many of the handhelds that report on APRS today have GPS built in to get your position automatically. Older radios, or those that don't, can have an external GPS gadget added that uses the NMEA standard. They mentioned here for under $99. I've not checked prices, but perhaps that's true. At any rate, you put the GPS information, then increases the accuracy of the reporting of our positions. How do APRS stations relay the data? By using digipeaters. We send it to a digipeater, it retransmits it with a lot more power to a larger collecting digipeater where it goes onto the internet. How does the packet path wide 3-1 designate? What does that designate? Basically, it designates how many hops have been made so far and how much remain to be made as this thing goes back and forth, sending the data from our repeater to another repeater. I might also mention that the McKinney Club does have a digipeater located up in Melissa, and it does exactly this. It will take your APRS data and retransmit it so that it can be picked up by a larger, more powerful digipeater someplace in this area. I'm not sure where that is, but then it goes from there into the internet so it can be tracked. On what frequencies are spread spectrum transmissions permitted? It's the new topic we've not talked about before. Spread spectrum is a frequency hopping type technique where the transmitter and the receiver know to jump from one frequency to the next, and back in order to avoid interference from various other services primarily. So what frequencies can we use spread frequency on? Anything above 222 megahertz, which rules out 6 meters and 2 meters. Okay. What describes the spread spectrum frequency hopping? Wow. Varying the frequency of a transmitting signal according to a pseudo-random sequence. And again, this sequence of the frequencies that will be used, the transmitter knows and the receiver knows as well, so they can stay in sync with one another. What spread spectrum communications technique uses a high-speed binary bit stream to shift the phase of an RF carrier? Called direct sequence. That's, again, one just need to memorize the answer. I don't know an easy way to explain that. Why are received spread spectrum signals resistant to interference? Because they basically don't pay any attention to the other things that are out there. The other things that come in are suppressed. We don't tend to hear those. Which of the following cannot be transmitted over an amateur radio mesh network? This is kind of a little bit of a tricky question. The radio mesh network really is not the important part here. It's how can we not transmit? What are we prohibited from transmitting? And the universal answer is anything that's encoded to obscure its meaning. That includes on any form of transmission, not just the mesh network. The exception you might remember is transmitting to a satellite receiver of some sort in which we send control sequences. Those can be encoded in order to prevent other people from messing with that satellite receiver. But generally speaking, messages that are encoded to obscure the meaning cannot be sent over any amateur radio frequency other than that. Which of the following frequencies can be used for the amateur radio mesh networks? Basically, we use a lot of the things that the wireless data services use, specifically the Wi-Fi services, 2.4 gigahertz and 5 gigahertz are suspects for using for mesh. Okay, what type of equipment is commonly used to implement a mesh network? We basically just used a plain old wireless router. In times past, there was a Linksys router that was very well known because it was easy to reprogram, and it was very much in demand by amateurs. It could be reprogrammed easily with the mesh firmware and would allow that to establish the connections between other mesh routers, which is one of the characteristics of a mesh network, is they will tend to seek out the other mesh routers that are in that nearby and establish the links that are necessary in order to provide communication from point to point. Okay, what technique do individual nodes use to form the network? Just plain, let's see, well, I'm getting ahead of myself here again. This is where the discovery and link establishment comes in. The firmware that's programmed into those wireless routers allow them to discover the other mesh stations and to set up the links between all the different mesh stations that are out there. What type of addressing do nodes use? And this is what I was getting to too early. It's plain old TCP/IP, standard internet protocol. Nothing special about that one. What indicates the delay between a control operator's actions and the corresponding change in the transmitting signal? In other words, what's that delay time? It's called latency. How long it takes from the time we send it until something happens is the latency. Which of these digital modes does not support keyboard-to-keyboard operation? That is to say, we can carry on a two-way conversation. Really, obviously, we can. That's for teletype. PSK31, obviously, we can. We do conversation on those, and also MFSK16 is similar to PSK31 in that sense. The Whisper network, however, is a one-way network. We send digital signals to that in order to see how far our signal is going and how well it's being received. It does not respond, hence it's not keyboard to keyboard. What factors affect the bandwidth of a transmitted CW signal? The keying speed, how fast you're going, and more importantly, the shape factor of the waveform that's created when you key down. That is to say, the rise and the fall time of that particular shape. If we looked at the output of the transmitter on an O-scope where we can see it, we would see when we push the key down that the transmitter comes alive. It sends a signal. When the key drops out, then it drops off. How quickly that signal starts up to full strength and how quickly it goes from full strength back down to zero is the rise and fall times on those. If those are too sharp, it creates a problem for us. The approximate bandwidth of a 13-word per minute Morse code transmission is 52 hertz. There's a formula for that, as we can see here. Again, there are not a lot of questions about this, so the 52 hertz answer probably is easy. It's just memorized. But if you want the formula, we take the baud rate times the words per minute times the fading factor, which you have to know. For CW, the fading factor is 0.8. But at any rate, 52 hertz is the answer. Probably easiest just to remember that. What is the primary effect of an extremely short rise or fall time on signal, the CW signal? The rise and fall time, again, is what we're saying when we key down and the transmitter comes up. If it comes up very, very quickly, and we're looking at that on an O-scope, we'd see an almost instantaneous rise from 0 to full strength. And likewise, the fall would be instantaneous back to 0 for all practical purposes. When that happens, if it's too fast, then we get the key clicks. We start hearing the click sound that comes from that rise and fall. Most common method then to reduce the same key click would be to increase the rise and fall times. Now, this is one you got to watch out for. Reduce the keying waveform, right? Sounds like that we'd want to reduce, but in this case, we want to increase the rise time, increase the fall time. Take longer to raise the signal and longer to let the signal deteriorate back to 0. So A is actually the answer there. That's a little bit tricky one to watch out for. And that's the end of that one. With that, let me kill that and go back to not sharing. And we will switch slide decks and come along for the next session, which is modulation, which is an interesting subject that you never realize how many different ways we can modulate a transmitter. Hang on while we change the slide deck. So the recording is now started as we start this one. So at least it will be in the right, this part will be good anyway. I'll have to go back and re-record that first, that other part. But anyway, going on from there. Picking up the next one, let me share my screen again. We're going to go to that one. And the modulation, let me be sure we're on the right thing. Yep, that is correct. Okay, we're going to go through, since there's quite a bit of technical stuff here, there are not all that many slides by comparison to some of the things that we're doing, or that many questions. We're going to talk about these things first, and then we'll run through the questions. I think that will serve our purpose best. Let me get a couple of things moved out of the way for me here. Okay, in an FM signal, the amount of deviation, you remember that in frequency modulation, we're taking an audio frequency and changing the output frequency of the transmitter in step with the audio. So the amount of deviation determines the loudness of the signal, the amount that we move the transmitter signal back and forth, that we increase and decrease its frequency. The amount of deviation determines the loudness of the signal, the modulating frequency, that is the frequency, the audio that we're talking about, determines the spacing between the sidebands and gives you the actual voice information that we're looking for. For any given modulating frequency, there's an optimum amount of deviation that can be accommodated for a given bandwidth. The relationship between deviation and modulating frequency is a complex operation defined by Bessel functions, which is a whole other discussion. Different services do different things, as you would probably expect. But anyway, FM is a great thing. Deviation is a good thing. Generally speaking, in most applications, a 5 kilohertz deviation is considered the maximum. And generally, we're operating a little bit below that in the things that we do. Bessel functions, just in case you want to know what that was, I grabbed that real quick and threw it in here. Mathematical functions that appear in problems involving wave motion and so forth by the French mathematician Bessel. Just an FYI. This is a little picture there of a spectrum analyzer showing a signal in the top left of that scope, or that little screen there, showing a signal of some sort. I'm not sure what it's showing. I can't really read the text that's in there. Anyway, on this particular question that goes with this, the E8B02 question, the word not is in there, which what messes it up and makes it not correct, if you please. When you calculate the modulation index, you do not look at the actual RF carrier. When you're looking at modulation index, we're looking at the amount of deviation in the transmitter and the amount of the audio frequency that we're dealing with. We're not looking at the actual carrier frequency, so that's why that's a not. And that particular thing. Okay, then there's a question about the two frequencies. To get the modulation index, we divide the peak deviation by the modulating frequency, and that will tell us what it is. So if our peak deviation is 5 kilohertz, and our modulation frequency is also 5 kilohertz, we would have an index of 1. And you can see where that would go. Obviously, they're using 3,000 and 1,000. So 3,000 by 1,000 would give you 3. And that is the answer to that particular question when we get to that question. Again, they have two things going on here, 6 and a 2. So 6 divided by 2 is 3. Angle modulation. So anytime we're doing something with phase relationships, a sine wave carrier is varied by various angles, angles of or degrees of modulation to replicate the incoming modulation source below 29 megahertz. So we're saying the 10 meter band and below. The highest modulation index permitted is exactly 1. So we don't do a whole lot of FM, generally speaking, below 29 megahertz. And I suppose that's one of the reasons for it. It's important to set deviation ratio properly on the FM transmitter to prevent splatter. If it's got too much deviation, it will tend to create birdies on either side of your main frequency, which is called splatter, which will interfere with everybody and everything on the different bands. Deviation ratio is the ratio of the maximum carrier swing to the highest audio modulating frequency when you speak in the microphone. And a little more discussion of that. They have one here where they have a 5 kilohertz frequency swing and a 3 kilohertz modulating frequency. 5 divided by 3 is 1.67. An older instrument there. We used to have instruments that were strictly modulation measuring devices. Heathkit made one in one of their kits, as a matter of fact, that I still have. And all it did was you would just key the transmitter and it would measure the amount of deviation when you whistle into the microphone. At any rate, calculating deviation ratio, again, we're talking about that. 7.5 divided by 3.5 is 2.14. So we're just kind of running that one back and forth. Frequency division multiplexing. We mentioned this a little bit earlier. In that way, the transmit signal is divided into separate frequency streams or subcarriers. We mentioned subcarriers before. Subcarrier is a little carrier just off the main carrier that carries data. Information is modulated to a subcarrier, and then when it comes back out, that's removed from the subcarriers and combined where it needs to be and put back into whatever it needs to be put back into to give us either audio or data. Transmit signal divided into separate frequency streams is the answer for the question. As opposed to TDM, time division multiplexing. In time division multiplexing, we do time slots, and we'll have a few microseconds of time, and one signal will occupy that. The next few seconds, a different signal will occupy that, and the next time slice, yet another one, and so forth. So we're multiplexing. We're sending different signals essentially at the same time by using discrete time slots in which to fit that data. Now, we have a picture of that. The little thing that I emailed out to you has this picture in it if you want to go back and look at it, along with a pretty good write-up about this sort of thing. What this picture is depicting, on the left, we have 3 signals that we want to send out. They go through a multiplexer, a synchronizing signal so we can keep all the timing correct. Time slot number 6, signal 3 gets a little slice there, maybe a few microseconds. Time slot number 5, signal number 2 gets a few microseconds. Signal number 1 then likewise, and then we repeat that thing again, and it just continues like that, basically forever, being synced all the time. Goes through a demultiplexer, which splits those 3 out, puts them all back together again. And from our standpoint, as the receiver, we never know that happened. It works out quite well, actually. Okay. Analog to digital converters is another thing that we get involved with and all this sort of thing. When we're trying to send out digital signals or deal with digital signals, oftentimes we're starting with analog first, i.e. voice data. So changing an analog signal to a digital signal takes place in an A to D converter, or ADC, through a successive approximation. That's one of the primary ways it's done. There's some others there as well. Successive approximation, meaning it just takes little slices of the audio and assigns them a binary value and then puts all those together. When it gets to 8 bits or 16 bits or however many bits the ADC accommodates, then it will send out that particular binary stream. There's some other things out there, DDS, direct digital synthesis, that can be used. It does it a different way, but successive approximation is one of the cheapest, hence it's one of the most common. The front end of the A to D converter is an analog amplifier, usually just an op-amp. Op-amp is short for operational amplifier. It's a little integrated circuit. A little signal goes in, a bigger signal comes out. That's all that really boils down to. At any rate, that amplifier that's going to amplify something going into the ADC, the A to D converter, needs to be a very low noise amplifier, because any noise it generates or any distortion it produces in amplifying that signal will also get digitized. So we want to clean the signal as we can coming in before it's digitized, not adding extra garbage to it from a noisy op-amp or some kind of a signal that would distort, or some kind of op-amp where they would distort our signal more than we wanted it to be. Okay, it's a high quality A to D converter must have an amplifier with a very low total harmonic distortion and a very low noise floor. And this is just a little diagram of how that works out. Analog signal coming in, this could be voice, for example, goes through an A to D converter, comes out digital, goes through the DSP, digital signal processor, which has read-only memory and random access memory in order to store the data, and a program to process it. It gets processed, comes out, and goes to a D to A converter once it's been conditioned, and then out it goes. I'm sorry, we're taking it the other way here. Analogs coming in, they're showing it all in one place. Analogs coming in and then analog coming back out again when we do a D to A, digital to analog. In other words, we go the opposite direction to convert it back. Normally, you wouldn't do that in one place. You'd have one of that on one, half of that on one in the transmitter, the other half would be in the receiver. Fourier analysis, again, named for, I think, a Frenchman, if I remember, has to do with a lot of the digital signal processing that we do. Fourier analysis is probably the main thing that you want to remember. I think I just skipped a slide, didn't I? No, I didn't. Okay, we'll talk a little bit more about Fourier analysis later on. We don't get into it deeply, fortunately. That's an engineering subject, but we will mention it just ever so slightly. An oscilloscope, one of the great handy instruments to have. The great thing about oscilloscopes these days is they're not all that expensive. You can get a little handheld digital oscilloscope for 50 or 60 bucks now. Granted, they're not fantastic instruments. They're certainly not lab quality, but they will show you a lot of information and give you a picture of a lot of signals that they can deal with if their bandwidth is wide enough for them to do that. An oscilloscope shows the amplitude of a voltage or a signal. How big is that signal in respect to time, i.e. up and down in the y-axis, we have the amplitude, how big the voltage is. And in the x-axis, we have time, usually in milliseconds or microseconds or picoseconds or whatever it is it's calibrated to do for us. And over that period of time, we can see what that signal is doing. The little picture below there shows, first of all, a sine wave. Just the picture of the sine wave going above and below a reference line there. We can measure that with the oscilloscope. Time is going from left to right in this case. They're not giving us the time frame there, but for one time period, that T period, that might be 1 microsecond, for example. Could be anything. Again, they didn't tell us what it is. We could also look at a square wave, do the same thing, or a sawtooth wave or a reverse sawtooth wave, depending on how the sawtooth has been generated. But it lets us look at those kinds of signals that way in the frequency domain. In the time domain. A spectrum analyzer does the opposite, though. Spectrum analyzer also shows amplitude on the Y up and down axis, but it shows frequency on the X axis. So we're plotting amplitude versus frequency. And in the oscilloscope, we're plotting amplitude versus time. Any questions on that? Again, if you have a question or something, please stop me. Sawtooth wave has an immediate rise time significantly faster than the fall time, resulting in a backwards waveform that looks like a saw blade. Okay, I have to go back to that previous picture to understand. That's almost double talk, isn't it? If you look at waveform B, it's a very fast rise time and a slower fall time. That is not your typical sawtooth. The typical sawtooth is the A1, where it rises slowly and falls fast. But then this one is trying to say that, but it's not saying it very well. RMS, root mean square, of a varying voltage, an AC voltage, is the equivalent to a DC value that would provide heating or would provide work. So we might have an AC voltage that's 110 volts, but it might have an RMS value of something far less than that, which would be the equivalent as if it were DC. To calculate that, if it's a pure sine wave, we do 0.707 times the peak, or 0.3535 from peak to peak. Usually we just use the peak value, and that will give us the mathematical RMS value. Because it's sine wave, we can predict it. However, if it's not a sine wave, if it's a random wave, then all bets are off, and we needed an RMS AC voltmeter to give us an accurate RMS reading for that. Regardless of its wave shape, it has circuitry built in to average that, so we get the actual RMS, root mean square voltage, the working voltage out of an AC waveform. Okay, it's not easy to determine the ratio of peak envelope power to average power in the regular single sideband set, because your speech characteristics vary. My speech is different from your speech. My speech is vastly different from my wife's speech, obviously. We can use different speech compression techniques to even those out, to average those out, to make it easier for us. But generally speaking, without that, we have some great variations. We mentioned the term peak envelope power, normally called PEP, P-E-P. Peak envelope power is that peak envelope power out of single sideband, the peak power that comes out. Most of your meters that can read power will have an average reading and a PEP reading. But then, of course, what they're giving you, the peaks that come out versus the average power, as if it were DC coming out your antenna. When we talk about power output from the single sideband set, we generally use PEP or PEP power for that. Depending on your modulation, the ratio of PEP to average power generally is about 2.5 to 1. That's a generalization, of course, but it's pretty close. They suggest remembering 2.5 because it's close to the bandwidth for voice. Voice is normally limited to 3 kilohertz, so I guess 2.5 kilohertz is close to 3. And if you can remember it that way, by all means. But the ratio of PEP to average is about 2.5 to 1. That's the actual answer to the question. The little picture at the bottom, we're showing a system that's generating a single sideband signal. The lower sideband is filtered out. The carrier center frequency is filtered out, leaving only the upper sideband. And I'm not sure why they showed that here, but I guess it's interesting to have it there anyway. A reactance modulator causes the alternate oscillator to vary its frequency in accordance with its modulation. It's the oscillator that gets modulated, not the output of the radio. The modulator that's out there, reactance modulator, we vary a voltage out there using our voice, usually for some kind of frequency. And oftentimes we will use some kind of capacitance modulation for that, because we can get the voltage diodes that will vary with voltage, vary the capacitance with voltage. At any rate, that reactance modulator then modulates the oscillator and changes its frequency as it needs to make it frequency modulated. But it's the oscillator that gets modulated. The output of the radio is just outputting whatever the oscillator and its subsequent circuits are generating. Reactance modulators found in many FMs. We vary the inductance of an inductor or a capacitor, usually a capacitor because they're cheaper, to produce the phase modulation, PM, or frequency modulation of a signal. Basically, it's just a way of varying that frequency by varying the reactance in a tank circuit. Anytime you see the words frequency discriminator, you can tie that to signal detection or demodulation in an FM transceiver. We're dealing with FM reception normally when you see frequency discriminator. Preemphasis is a little thing that we came up with FM radios. FM radios tend to de-emphasize on their own the higher frequencies and emphasize more than they should the lower frequencies. So we use a pre-emphasis network which will attenuate some of the lower frequencies while amplifying some of the higher frequencies so that they will transmit more clearly, more distinctly over FM radio. Then when the FM receiver receives those, it will normally have a de-emphasis network that will restore that back to the original audio. That's essentially what we're talking about with pre-emphasis and de-emphasis. In a single sideband transmitter, a lower or upper sideband filter removes the unwanted sideband. We saw that in that little picture a little bit earlier. DSP, digital signal processing, does a lot for us these days, as you probably know. DSP relies on phase shifting the carrier of the audio components by 90 degrees and sending that into a single sideband balanced modulator, which will allow us to separate those sidebands out along the way. All of this quadrature occurs in the DSP chip. Quadrature, you remember, anytime you see that, think 90 degrees. And that's where we're back again. The DSP relies on phase shifting the carrier and the audio by 90 degrees. Quadrature. A Hilbert transform filter is a handy word. It's a DSP filter. Performs an operation on a signal. A signal containing both the I and Q, the in phase and quadrature components of it. It's a high-tech single sideband generation way of getting things done. And we'll see a question on that. Hilbert transform is the key to that as a DSP filter used for single sideband generation. Baseband, term that refers to the range of frequencies occupied by a message prior to modulation. For digicodes and CW, it'd be as narrow as 30 hertz. For voice, it'd be generally 3 kilohertz or less, for example. For FM, 2.5 kilohertz to 25 kilohertz worth of baseband, depending on whether it's using wideband or narrowband modulation. May your spurious emissions be minimum. Amen. FCC says it needs to be that way, and then they're very picky about that. Spurious emissions is random splatter, things that we generate that we didn't intend to generate. For example, as we said earlier, if we're overmodulating our FM transmitter, if our deviation is set too high, we would generate these spurs or these little frequency pop-ups on either side of our main signal. You'll see that in the picture that they have there. With a little scope, the tall signal is the main signal. That's the carrier frequency of interest. But it's generating some spurs on either side, as they're called. You can see those little frequency pop-ups on either side. And if one of those little frequencies just happened to be at the same frequency of a repeater that you like to use, then you would have interference with that repeater. And that's often is the case. Okay. FCC can impose quiet hours on your transmission for a specific thing. For example, if you're running a big amplifier and your neighbor complains and the FCC agrees with them, they can say, okay, you can't transmit with that high power amplifier between 6 in the evening and midnight when they're watching their TV or listening to their radio or doing whatever they're doing. Common emitter amplifier has to do with a transistor. We'll talk about that. We'll see a figure that illustrates that next. There's a common emitter amplifier. Common emitter gets the name because the emitter, that's the transistor with the arrow pointing down. That's the emitter. It's common to both the input and the output. Okay, and we're going to talk about that circuit some more as we go along. And there's several questions pertaining to this circuit on the test. A little bit of Thevenin's theorem. We'll talk about that in a second. Theorem's theorem, as you see there, a little thing engineers do. They simplify an equation. So basically, we'll simplify this circuit down to a power source and a resistance. That's all that really boils down to. Anyway, R1 and R2, which is over on the left there, perform a voltage divider or create a voltage divider. Will give us a fixed voltage on the base of that transistor, which will set the operating range of that particular transistor or the bias for it. That will determine how much it conducts on either side of its center voltage that it would normally be putting out. And by adjusting that bias voltage, we can change the class of operation, which we'll see here in just a minute. We'll talk more about that here in just a minute. Anyway, R1, R2 form a voltage divider to set the base bias. Then R3, the resistor down off the emitter, will also have a small voltage drop when it's working. That's called base emitter bias voltage. It also affects the base bias as well. It's part of the settings when you're designing these circuits. R1, R2, and R3 are designed such that it will provide the right voltage on the base of the transistor, consistent with that particular transistor's characteristics. And if we're looking at the voltage produced off R3, that's called self-bias. Okay, networks. Pi network gets its name from the fact it looks like the Greek symbol pi. The first one there, the pi low-pass filter in the first picture there, you'll see has two capacitors and a coil. It looks like the pi symbol, basically. Low-pass filter. The way you can tell a low-pass and a high-pass filter. The low-pass filter is going to use a choke or an inductor to pass the lower frequencies. A high-pass filter will use a capacitor to pass the higher frequencies. So in this particular pi low-pass filter, the higher frequencies are siphoned off by the two capacitors, and the lower frequency is allowed to run through the inductor. That's the idea behind it. And then we have several variations of filters along the way. A T-network high-pass filter, you notice, as we said, the two capacitors are going to pass the high-frequency signal right on through, and the little inductor that's there is going to siphon off any low frequencies so that they don't go through. Only the high frequencies get through. Then conversely, the low-pass filter right next to it, we have an inductor which allows the lower frequencies to go through, and a capacitor that siphons off the higher frequencies. Another variation on that, using a pi for a low-pass. Pi network, where we have a tunable filter, and then a pi L. The L, you notice, it looks kind of like the letter L inverted. We just added a coil on the output of it. And then we'd also do a T-network low pass. Again, you notice there's two coils there. The low frequency signal will pass through the two coils. The high frequency component will be drained away to ground through that capacitor. Okay, a lot about filters. We'll see some more of that as we go along. I think we're going to go through this. We'll wind up stopping at 8 o'clock and actually get into the questions next time. Also, the thing that I emailed out to you contained the little schedule that I showed you, I think, before. We do have some time, especially as we get more toward the end of the sessions. We have some places where we don't have a lot of questions, and so we have some makeup time really built in. So if we get behind, it's not going to hurt us that much. Okay, T-networks, high-pass filter. We pretty well killed that subject already, I think. Talking about the pi L, remember the L? The inverted L looks to this thing. This would be a low-pass filter because the low filter is going to pass through the two coils. The high frequency would be drained off through the two capacitors. Pi L is an additional inductor at the output. That's the L on the right on the output side. Emitter follower, the common collector amplifier, sometimes called an emitter follower. When you see it drawn, the collector looks like it goes to ground instead of the emitter. Sometimes called an emitter follower because of the way the voltages act in that. Often used in oscillator circuits, and it has a very high input impedance but a low output impedance. Now, a high input impedance is very important when it's attached to an oscillator circuit. If a low impedance something or other is connected to an oscillator, it will tend to pull the oscillator frequency down. It will tend to change the oscillator's frequency. To avoid that, then the emitter follower works well because of its high input impedance. It doesn't drag the output down, and yet it will still bring the signal through, and then that signal can be distributed to other places without affecting the oscillator itself. We'll watch the time here. Some of the older radios could vary the matching network to cancel reactive part of impedance and change the value of the resistive part of that fluid impedance, i.e. we had variable resistors, variable inductors where we could change back and forth along the way. The newer ones generally, or at least oftentimes, have built-in automatic antenna tuners, which will do that for us automatically. They will basically switch in the right capacitors or inductors as necessary to compensate for that rather than our doing that manually. Intermodulation or intermod. occurs in the repeater's final amplifier. That's when something close to your repeater, a signal close to it, transmits and mixes with your signal out of the repeater, and you get the sum and the difference frequencies that come out, causes significant noise on the repeater's own frequency, as well as generating some spurs and interference with other things. Intermod interference minimized by careful selection of the circuits. Nonlinear circuits, devices, and components are where we look for problems if we're having intermodulation issues there. We're having these noise and spurs pop up. This happens with Echolink. Those of you who may wonder about Echolink, our Echolink system is here at my house. The radio is a Kenwood, and of course it has built-in necessary pieces there to hook directly to the radio, and then it also hooks to the internet. So basically, when I transmit, it swamps the receiver on the Echolink side. And so anybody that's listening on Echolink hears garbage because that radio its receiver has been desensitized. It's been swamped. Conversely, when somebody talks on Echolink or talks and Echolink is broadcasting, then my radio goes ballistic and I can't hear what the people are saying there because my radio gets desensitized because they're just too close together. And then one overloads the other in its receivers. The receivers are not good enough to separate those out at those frequencies. Cavity filters are a big thing with repeaters. There's kind of a picture of it there. Usually you'll see more than two, though. Usually you'll see 3 or 4, and they'll all be put together. And somebody just entered. We'll let him in there. The cavity filters are great big filters. They're big can-looking things that are tuned. And they allow us to be able to transmit and receive on a single antenna with 2 frequencies that are only 600 kilohertz away from each other, as opposed to my radio here and the Echolink radio, which doesn't have that kind of filtering and it gets overloaded. So that's how a repeater can work with one antenna and be transmitting and receiving at the same time on that same antenna and not have the transmitter overload the repeater's receiver. The incoming signals that normally would overload it are filtered out by those cans or those cavity filters so that the receiver doesn't see it. Or doesn't hear it, I guess is the right word. Let's see. One of the solutions for solving intermodulation, use a terminated circulator or a ferrite isolator out there to quell that spurious signal that you don't want. What is a terminated circulator? A 3-port device. I've never seen one, by the way. 3-port device for RF allows signals to flow in one direction, and it siphons off basically the unwanted signal so it doesn't go out the output port. That's kind of it in a nutshell. Terminated circulator. Common mode currents are what they imply, currents that are equal in amplitude phase on 2 or more conductors. Best way to reduce common mode currents, you use a common mode choke. We use a ferrite toroidal type choke. A string of ferrite beads over a coax, for example, will tend to quell common mode currents. Okay, good. That's exactly where we need to be. It's 8:01, and we'll pick it up at this point next time at the same place. Okay. Wow, everybody's been quiet. I don't know if that's good or bad. Any questions from anybody?
No, sir.
You're easy. Okay.
Not tonight.
Am I going too fast?
No.
Okay.
It's a little overwhelming, but I'm okay.
Okay. The real secret, again, is to get some insights from this, perhaps, and then do the practice test online, and you'll start to see those things come together. And your brain will just see that the right answer. It'll just go, zip, it's a letter A or it's letter C, or your eye will just fall on it and know that's the right answer. Once you do the practice test, it'll all start to come together. Of course, that's always what we want anyway, isn't it? Okay. Any questions or any comments at all from anybody? I did send out the email. One of you, I believe, said you would send me your email address. If anybody else hasn't sent me your email address, if you'll just email me so I have your address, I'll add you to our list and make sure you get anything that we send out along the way. Easy address is K5CRXHam@gmail. That's easy to remember. My call sign ham@gmail. And I'll get that and I'll put your name on the list. Well, with that, gang, it's been great. I appreciate your patience and you're putting up with me. And if you'll join me again next week, same time, same station, we'll do this again. We'll continue with the questions on this part about the modulation and all that, which is kind of a technical subject, as we said at the beginning. But we'll pick up the questions on that, which will be a review in essence, and I think maybe nail it down for us. So with that, unless there's anything else to be said, good night, everybody. Anybody have anything, any parting comments?
Thank you, Bob.
Thanks,
Thank
Bob.
you, sir.
Thanks, Bob.